Now let's see what a single trie node looks like in memory. You will see why one node is surprisingly expensive. Let's look at one trie node in the heap. It holds 26 pointers, one for each letter, plus a small integer flag. That is far more than a list node with one pointer or a tree node with two. At the top of the card, which is the highest address, sits the isWord flag. In the struct it is declared last, after all 26 child pointers. Right now it is 0, so this node is not the end of any word yet. Below it are the 26 child pointers, one per letter. Most of them sit empty. This gap stands for 22 more pointer slots we are not drawing. The pink row is child at index 2. The slot for the letter C, it is the only slot that points somewhere. It holds the address 2000, which is the node you reach by following C. Child at index 1 is the slot for the letter B. It is null. No word here uses the letter B at this position. Child at index 0 is the slot for the letter A. It is also null. So 25 of the 26 slots are empty. Let's add up the cost. 26 pointers times 8 bytes each is 208 bytes. Add the 4-byte isWord flag, padded to 8 bytes, and one node is 216 bytes. And only child at index 2, the letter C, points anywhere. 25 of the 26 slots sit empty, still costing 8 bytes each. Compare that with the binary tree node from Chapter 9. That one was only 24 bytes with 2 pointers, so one trie node costs about 9 times more. One reminder, these addresses are for teaching only. They are never the real output of the allocator, as we saw back in Chapter 4. There are two ways to store a node's children. In the array form, every unused letter still costs a pointer slot. Another way stores only the children that really exist. Let's compare them. The first way is the 26-slot array we use in this chapter. Access is big, O of 1, because you index straight to the letter. But every node always pays for 26 slots, and most of them stay null. It is fast and simple, but wasteful on sparse tries. The second way stores children in a small sorted list or a hash map. Access is big, O of log k, or big O of 1 on average, where k is the number of children present. Now only the children that exist cost memory. It is compact but slower per step and more code. This course uses the array form, because a to z is small and fixed, and direct indexing keeps insert, search, and starts with simple. Real dictionaries with huge word lists and larger alphabets usually switch to the compact form.